Hello, my name is Brittany Holmes. I'll be discussing the workflow for accomplishing continuous surface modeling. The goal is to share tools within Rhino on how to analyze and correct curvature for tangency, as well as evaluating surface continuity. With this type of understanding, the same method can be applied to site, roof, and ramp design. So with that being said, our model will end up looking something like this, and I hope you follow along. To get started, open up Rhino 7 or whichever is the current software version of the time you're viewing this, and set your graphic display to ghosted. To do this, click on the viewport title in both the perspective and top viewport menu, and then select ghosted from its display menu. This display view will help us easily see our foundational work, and then we can later toggle back to the Arctic display in our viewports to evaluate the geometry. Before we create the framework for the reception desk, double-click on the layer curves, or right-click by clicking Set Current to make this your default layer. I've also included 2 additional layers that we'll use later that you can mimic or rename to accommodate the geometry that we will create. We're now ready to get started by drawing the floor plan for the reception desk. What I've done is I've included a couple notes in the note tabs, which you can access from the options wheel, and then select notes. And here you'll see what the overall objective is. We want to accomplish a 44-inch standing counter, a 34-inch working counter, and then a 28-inch counter that someone could sit at. And the consistent depth of that counter is going to be 24 inches. You'll notice in the status bar that the units is set to feet. However, Rhino will understand and convert any units that are inputted into the model. So for us to accomplish 44 inches, all we would have to do is type in 44 inches with the symbol there, and Rhino will understand what that height should be. In the top view, we're going to start to draw the boundary of the reception desk, and what we can do is we can either click polyline, or you can do control points through curve that was previously demoed. For this purpose, let's go ahead and try a different method by clicking polyline, or you can also navigate up to the curve, select polyline and polyline. I can go ahead and make one edge 15 feet, the next can be 20 feet, and then we'll wrap it around with a 5-foot kickback. I'm going to go ahead and type in fillet corner. I'll follow the prompts in the command. And 2 foot is fine, and you see how it nicely does that for me. At this point, I'll go ahead and move this to 0, 0, 0, and then using a shortcut, zoom extends, I'll go ahead and just make it the full screen. If you recall, one of our parameters in the notes mentioned that the counter depth was going to be 24 inches. So from here, we'll go ahead and offset our curve. And what you'll want to do is select cap and flat. And then the distance is going to be 24 inches. And what this will do is it will enclose your offset rather than having to generate an edge condition to then join, so that way it would be a closed poly surface. So let's go ahead and fillet the inside condition as well. So I'll repeat that command, select the object, and then I'll reduce the radius to 1 foot. At this point, we need to divide the reception desk into 3 pieces based off of our notes. So we want 3 different heights, standing, the desk counter, and the sitting piece. So if you navigate to the toolbar and select polyline, go ahead and draw a line of where you would like the polyline to be split. And so this could be one zone, a secondary zone, and a third zone. So at this point, you can type in split, the objects to split, and then what you want to cut by. Having split the reception desk into 3 pieces, we can now extrude. So you can select the area you'd like to extrude while clicking on the gumball, and then select the ball in the center in the Z direction to extrude it the 28 inches. We can also select the next piece and in the command bar type extrude as an alternative method for extruding. The gumball works perfectly fine, and this one can be the standing one, so we'll extrude it 44 inches. And the last piece, we'll go ahead and extrude it 34 inches. Now that the initial geometry is set up, let's define the seaplanes to easily access different elevations in both the X, Y, and Z construction planes. The seaplane command sets the origin and orientation of the construction plane in the active view port. So what that means is the construction plane actually represents a local coordinate system for that specific viewport, and it can be used in different world coordinate systems. Let's go ahead and define the three different elevations for the reception desk. And first we'll need to go ahead and create a new layer. You can either right click and click new layer, or there's an icon located here, which is also new layer. So let's go ahead and label this seaplane. I'm going to double click it to make it default. And then here I'll make a height of 28. And what I'm going to do is extrude this and then go ahead and copy it to the 44-inch height and then the 34-inch height. There are two different locations where you can set a seaplane, which will help you draw on that specific construction plane. One is located in the Named Seaplane tab. You can click the Options wheel and then navigate to Named Seaplanes, and that's how you can have it populate here. So this window will show you a list of seaplanes that are saved specific to this project, and in a way to do that is set the seaplane by clicking Seaplane tab up here below your command bar and then clicking Set Seaplane to Object. So if we zoom in, we can go ahead and set our object to, or our seaplane to this object, which is defined by our three different heights. And then from here, you'll go ahead and hit save, and then you can say seaplane, and this was the lowest one, so it's 28 inches. We're going to go ahead and replicate this another 2 times. So now we've elevated the seaplane up to the 44 inches. So seaplane 44 inches. And then one more time to the 34. Having created our working construction planes, let's duplicate the edge of the reception desk surface to begin developing the countertop geometry. This geometry will serve as a smooth transitional surface between counter heights. To do this, we'll duplicate the edge along the reception desk, and I'll go ahead and make this enlarged so we can see it a little bit better, as well as changing it from ghosted to wireframe. In the command bar, you'll type in the command dupe edge and select the top counter surface. And then for visualization purposes, you'll also want to select the bottom because we'll eventually turn on the control points and speak more to the tangency connection between the upper and lower counter surface. When you're done, you'll press enter, and then you'll navigate over here and turn on your points. The tangent direction is controlled by the relationship between the vector of the second control point and the end control point. Therefore, it's not possible to achieve tangency with only 3 points along this curve. To fix this, we can adjust the degree of the control points by using the command change degree. What you'll want to do is follow the prompts by selecting the curves you'd like to adjust the degree and press enter when you're done. We want to adjust this degree 2 curve into 4 points by making it a degree 3. So here you'll just add the number 3, and then you'll see that we now have 4 points. Therefore, a degree 3 curve, which is a minimum of 4 control points, can each have a set of tangent directions without affecting the tangency at the other end. As mentioned, the second control point and the end control point makes a vector that controls a tangency, and the connecting curve, which is our upper counter, needs to follow that vector along the target line in order to remain tangent. We can illustrate that line by connecting the second control point to the end control point, and then by using the command set point, we can select the second control point and the end control point of our connecting curve to our target geometry, which is below. So in the command bar, we'll type set point, and then we're only interested in moving it in the Z direction. And you can see here, we'll go ahead and snap to the end. Therefore, because both of these points, the second and end point, fall along this vector, we know that the two curves will remain tangent to one another. We can go ahead and delete the curve that was indicating the vector between the second and the end point. And to verify the position of these points, we can use the command gcon to verify the difference in position, radius, tangency, and curvature between these two curve endpoints. So we can follow the prompts and select the first endpoint and the second curve. And you'll notice that the curve RG1 result achieves tangency measured by the position and curve direction at each end. Now we can go ahead and generate the transitional countertop surface by lofting these two curves. So what we'll want to do is type in loft, and before we select anything, we'll want to navigate down below and click record history, which will be discussed here in a minute. Back to the command bar, it's asking us which curves to loft, so we'll just select the one on the left and then the one on the right, and when we're done, we'll press enter. The loft option default settings are correct, so you can go ahead and hit OK. I'm going to change the display from wireframe to ghosted so we can demonstrate the power of record history. So by double clicking on perspective, we'll go back to viewport or for viewport display. And if I want, I can select this point here and move it backwards. And you'll see that the loft command remembers the curve information. And then trim the extrusions with the loft to start sculpting the reception desk. So in the command bar, type in trim and then select the edges that you no longer want to remain. We can continue to build out the rest of the reception desk counters by lofting. Now that we're done lofting the rest of the countertops and have assigned the newly generated surfaces to the correct layer, we can now analyze the tangency between the countertop surfaces. In order to do so, we can use one method, which is the zebra command. Zebra visually evaluates surface smoothness and continuity using stripe map. This technique helps authors visually analyze the surface smoothness, curvature, and will also detect any anomalies that may contribute to discontinuity. So in order to do this, we'll select the countertops that we'd like to evaluate and then prompt the zebra command. After doing this, we'll want to navigate to the option dialog box, which will provide additional settings to customize the visualization. So depending on the geometry that's being analyzed, the stripe direction, which can be located here, size, which is thick to thinnest, so you'll see that we currently are setting as thinnest, but maybe if you are working on a larger scale, you can adjust your thickness here, as well as color. And also you'll notice that some of the stripes are not necessarily super smooth. So what we can do is adjust our mesh. After clicking the Adjust Mesh button, this dialog box for detailed options will show up, and your settings may look like this. Within the detail options, we can change the minimal initial grid quad from 0 to 5,000. This number is recommended by McNeil to generate a fine and accurate mesh. So depending on the complexity of your geometry, you may want to double this, or it just really depends on how it visually looks along the geometry. The rest of the settings in this option box are good, and now we can just click OK to close out of this. Having increased the mesh density, we can now evaluate how the stripes are falling between the three selected countertop surfaces. If the stripes line up as they cross the connection, but turn sharply, which can be seen here and also here, then the position and tangency between the surfaces match. So that's what we want. And this also indicates a G1 position and tangency continuity between these surfaces. So it's a little bit easier when we highlight the geometry to really see that it's relatively smooth between these transitional surfaces. So with that analysis, we can confidently move forward knowing that the continuity between these transitional surfaces are tangent. In preparation for the next step, we'll just go ahead and join all of this geometry. That's fine. And then we'll also make the massing our default layer. Next, what we'll want to do is fill out the edge by typing that into the command bar and then selecting the edge along the parameter of the reception desk. Before I click enter, I'm going to make sure that the radius is 1/2 inch and then click OK. Next steps will be assigning materials to sub-selected surfaces along the counters and choosing a render engine of your own to finish out the visualization. To add a material, you would navigate to the Material tab, and then you can either create a new material or load a material library. And because this whole thing is joined, we can do a sub-select by hitting Control Shift and selecting the surface that we'd like to apply material to. And then right-clicking the thumbnail, you can assign to objects. So to visualize that, we can go to Arctic Display and you'll see that there's a new material applied there. And depending on your preference, you can use a render engine to really flesh out the visualization on your design intent. So with that being said, thank you so much for joining me. I hope you enjoyed this tutorial and looking forward to the next one.